Hello, everyone. We are Zhang Haiquan and Rhettxie from Tencent Security Unit Laboratory. We are senior security engineers in the lab, and we are very honored to have an opportunity to speak at Black Hat. Our presentation is titled CodeQL, also a powerful binary analysis engine. The entire presentation is divided into two parts. The first part, I will give you some introduction of the fundamental of CodeQL. And the second part, my colleague will explain how to extend CodeQL to support binary analysis. The outline is displayed here. We will first introduce static analysis and what CodeQL is, then introduce its core technical points, including architecture, engine, and the query language, and explain how to make it to support binary analysis. In order to achieve this goal, we are developed a dedicated debugger. Finally, we will show a demonstration. Here we go. The story begins with static program analysis. Static analysis is a key technology in the field of security. It's very interesting, but also very challenging. Static program analysis is the art of reasoning about the behavior of computer programs without actually running them. And an analyzer is a program that reasons about the behavior of other programs. You can see that write a program to reason about other program, but without running it, it cannot be an easy task. For several decades, many issues have been resolved, but many problems still left. Precision and efficiency are the two big problems. In a long period of time, many amazing technologies have been developed. For example, type reference and abstract interpretation. In the real world, our brains are constantly making abstract interpretations. Data and control flow analysis, point analysis, path-sensitive and content-sensitive analysis, constraint solving and sampling execution. At the same time, some amazing tools have been developed. Here is a table. We list some of the most popular and famous tools. But what is CodeQL? It was a research project at Oxford University, founded in 2006 and acquired by GitHub in 2019. As you know, GitHub was acquired by Microsoft, so CodeQL is now belongs to Microsoft. It's partly open source, but the core part, for example, the engine, is not open source. CodeQL's basic working mode is to scan code, make database, and run query logic, find code patterns. So CodeQL made code analysis to code property query. Okay, let's take a look at the architecture of CodeQL. CodeQL is a collection of components. The extractor, database, query language, compiler, core engine, and a lot of libraries. The extractor can be regarded as a language fountain, so its language depends. Extractors cast code, make extra analysis, and store code properties to database. Database store code information can be shared and reused. CodeQL introduced a query language. The QL is related with query logic, but not related with code that building analysis. So its language is agnostic. CodeQL has developed a mature and comprehensive library that can perform various data flow analysis, such as the classic tent analysis. The core engine can be regarded as a database evaluate engine. That's the architecture. Now let's see how it works. This is the command. This is a command to create a database from QEMU project. We know that QEMU is written in C language, so it needs to compile. For compile the language, the extractor and the compiler will work in parallel. The extractor monitors compiler works. If it failed, then the process will abort. Otherwise, it intercepts compiler's commands and adds more parameters. Extractor needs to know the parameters of the compiler because it has to know which header forms and the library forms should be included, and which forms won't be compiled. In the left, this is a snapshot taken during compilation, showing an illustrator process working at the same time. Its parameters are very similar to these of the compiler process. But how does the illustrator interrupt the compiler? We did some reverse engineering on CodeQL. Its core engine is written in Java, so it's not very difficult to do some reverse engineering. We can see that at the beginning of the compiler process. Compilation process, CodeQL launched a preload tracer process. We also did some reverse engineering on that process. This sampling code shows that preload tracer will inject something into LD preload, and GDB told us it's injected lib tracer.so to LD preload. So every newly created process will load the lib tracer module. Lib tracer module detects whether the host process is the compiler process. If so, launch an illustrator process. Use the parameters of the compiler process and add some more parameters. The parameters which are added to illustrator process are obtained from a configuration file. The configuration file is named compiler tracing.spec. This is how illustrator launched. Now let's talk about the database. In fact, illustrator generated a travel file firstly, then converted the travel file to the final database, but not generate a database directly. Here, we have to mention another important file, dbscheme. dbscheme is a guidance document for the content extraction. Illustrator extracts information according to this file. First of all, let's map all these files together and see an example. The left diagram is the source code. We will do some tests. The central diagram is the travel file, and the right diagram is the dbscheme file. Illustrator scan code extracts information described in dbscheme, and the code information extracted out will be placed as a travel file. Travel file is a text file. It's not convenient for further process, and it will be converted to a structured DB file. Let's explore the dbscheme file. Take a look at the left diagram. Functions is a collection of all functions. It has a Unicode name label at function can be referenced by this name, and it also has two fields, name and count. We can see that the name is string and count is an int. Count 1 means it's a normal function, and 2 means a constructor. Another example is a little complicated. It's a statement. Its reference name is at stmt. It has two fields, count and location. Count means count of the statement, and the location is the position of the statement in the source code. It has start line, start column. Take notice, location is a reference to another type. Now let's explore the travel file. In the left diagram, functions record all the functions defined in test C, and 193 is an index. It records the function name, and its name is the string xopen. Its kind is 1, which means it's a normal function. Another example is a statement. Its kind is 6, which means a return statement, and the location is 16, 11. If we check that location at test C source file is really a return statement. So as we said before, the extracted code information are all stored into the travel file, and remember, it's a test file. How does the travel file be converted to a data file? Database file is a key operation. The function name of xopen will go through some encoding and become a number value. Then other information about the function will also go through a similar encoding process, and the entire function will ultimately become an int tuple. The tuple will be written to a database finally. Look at the IEL files. That's the real database file. and take a look at the content I have circled. They are the hex format of the function information mentioned earlier. So the int value in tuple can be regarded as the index to the actual results. But how to locate the actual results from index is a complex and tedious process, and we will not go into further details here. Okay, now it's time to talk about the query language. The query language is a declarative logic programming language with class and OOP support. It's target language independent, which means you should only focus on query logic, but not the target language type. And also, CodeQL has developed many built-in libraries, such as most common data flow analysis, trend analysis. The diagram on the left shows the layer of the query language. Firstly, the query language code will be desugared and converted to Datalog language. In CodeQL, it's named DIL. Then the compiler will do some optimize and lowering. DIL converted to RA. The RA is used commonly in SQL language. And QL to DL is first the lowering phase. The first diagram is a simple QL code example. It's very simple. It lists all the functions that will call DL open function. It will be compared to DL. And at the same time, some of the DB scale files will also be compared to DL codes. So as a whole, it's a lowering process, high-level user-friendly language compared to motion-friendly language. In QL source code, we can see select from where. After compile, this kind of high-level query language converted to table queries and full calculus. The second lowering phase is DL to IA. Is the continual lowering. Data logic had been compared to IA operations. In IA code, we can see classic join unit operations, and we can see R1, R2, R3 is not registers. We can regard it as temporary results. IA operations are already very low-level set operations and bulk calculations. Okay, the final component is the evaluation engine. IA code are executed by this engine, but IA code is not executed one by one. A set of logic related together and cannot be separated. This set of IA operations is called a query tree. The engine will consume a tree at a time. The IA operations listed on the left diagram is a query tree. It will be executed from bottom to up. The engine of CodeQL supports recursion evaluations. After this evaluation, R5 in our example, a DL open function query will be done. Okay, it's time to sum all things up. CodeQL has several language functions as executor. It extracts code information to analysis and store information to database. CodeQL implemented a Datalog query language to query code property. CodeQL stores code properties as database and regard code analysis as database query. After introducing so many implementation details about CodeQL, we can figure out the advance of CodeQL's approach. The architecture design is very elegant, highly modular, and separated the front end and backend. CodeQL is a feasible implementer of database technology, convert code analysis to data query. Well-designed query language focus on code pattern or semantic matching. One query language can handle many other code languages, thanks to a unified query language. The same logic for different analysis tasks can be reused on large scale. In the second part, my colleague Zhang will continue to introduce how to make CodeQL to support binary analysis. I will hand off the time to him.
Hello everyone, my name is Zhang. Let me introduce CodeQL for binary to you all. CodeQL is a tool with excellent architecture design that supports multiple programming languages. During the use of CodeQL, we had an idea to reverse engineer it. Through reverse engineering, we discovered that we could make it support binary file analysis and the existing closed source engine. That turns it into a universal analysis platform for both source code and binary files. To achieve this idea, we made some modifications to CodeQL's components. Firstly, we redesigned and developed a DB scheme for binaries to better adapt to the characteristics of binary files. Secondly, we improved the extractor to correctly extract key information from binary files. Finally, we developed a QL library for binary files so that users can perform more in-depth binary analysis using CodeQL. With these modifications and improvements, CodeQL for binary has become a powerful tool that can support the analysis of both source code and binary files. This enables developers and security experts to comprehensively review and evaluate the security and the reliability of software, whether it's source code auditing or vulnerability analysis of binary files. CodeQL for binary can provide strong support and convenience. Our design principle is as follows. Store the file architecture, string, and function info of the binary. Store the information of instruction registers and basic block inside the function. Store the use and dev information of register inside the function. Store the information of global variables and pointers. Store the memory layout information, address, section, etc. This section is about some details of DB scheme design, which determines what information the extractor needs to extract from the binary file, and what metadata the QL library needs to provide a complex functionality. The current version of the DB scheme stores file information, which means allows us to query relationships between multiple files. In addition, there is some basic information such as export functions, import functions, instructions, registers, and strings to support SSA and data flow analysis in the QL library. We also store information about the use and depth of instructions. The story of this information is crucial for the normal operation of extractor and the QL library, as it provides necessary context and metadata. Currently, there are already very mature decompilation tools available on the market, which means we don't have to develop a similar tool from scratch. In this project, we use Datalog as our extractor. The advantage of Datalog is that it supports a wide range of file formats and architectures, and provides a very rich API. This means that we only need to extract information from binary files based on the DB scheme, or without having to write our own parser. Another advantage of using Datalog as an extractor is that it has been widely used and tested, so we can reliably easily integrate it into our workflow. In short, use metric decomposition tool can greatly improve our work efficiency and accuracy, allowing us to analyze and understand the information in binary files more quickly. The above has completed the creation of two most important key components for creating a database. Now they need to be integrated into the CodeQL data creation workflow. Below is how we supplement the configuration file needed for the workflow through dynamic debugging. We have configured and registered a new language operation. Since we are doing binary analysis, there is no need to configure a compiler. However, the CodeQL engine internally checks for this file, so we need to create an empty one. Finally, we need to create a state file using the CodeQL data measure command. The main task of autobuild.sh is collect and compress the trap file generated by the Datalog plugin and copy them to the corresponding database directory for the CodeQL engine to read and generate the database. This process ensures that we can effectively use the data generated by the Adapro plugin and integrate it into the analysis flow of the CodeQL engine. In this way, we can better utilize the auto-build script to generate a database that can be used for CodeQL analysis. The current version of the CodeQL library is still in its early stages, but it already provides some basic functionality for query binary file information. This offers users a convenient way to obtain the required data. However, we also recognize the need for provide advantage features such as control flow analysis, data flow analysis, tint analysis, as well as support for AR, SSA, and cographs. Our initial idea was to port in features from other languages into binary stack analysis. However, during the porting process, we discovered that the information in source code is more comprehensive than that in binary files. Therefore, some modifications can be directly used, and we must be develop a new functionality specifically for binary features. Also, the current version has some limitations. We can continuously work to expand and optimize the QL library. Our goal is make it powerful and comprehensive tool that can meet various needs in binary stack analysis. We are well aware of the expectations users have for functionality, so we will continue to invest resources and effort to improve the QL library, ensuring that it meets users' requirements and provides richer and more comprehensive features. We believe that over time, the QL library will become an improved tool, offering users more value and convenience. And the usage of library in binary file is similar to that of libraries in other languages. This simple example uses the export function type provided by the binary QL library to query the name of all exported functions. Below is an example of writing a complex condition query using the binary QL library. We want to debug to help us better understand the library of QL language. Also, CodeQL has provided a relevant documentation. The code volume in CodeQL library is large, uses many syntactic sugars, and reading and understanding the algorithm implementation is very time-consuming, and the implementation intention can't be fully understood. Therefore, we develop an RA-level dynamic debug, similar to a traditional black box assembly debuggers. Our debugger can trace the details of QL programmers. We use VS Code as a front end and interact with JDB. JDB controls some key functions with reverse engineering by attaching to the JVM. In this way, we develop a debugger without source code to help us better understand the QL language and solve some bugs encountered in developing QL library. This is where we find the entry point for run RA. After QL language is compiled into RA, it's not executed in order of the orange code, but rather by calculating the dependency relationship between including the first two run are the tables directly referenced in QL, followed by the intermediate tables generated after operations on the data tables, and finally the operations or results obtained from these intermediate tables. This entry point not only allows me to control the execution and the path of RA, but also obtain the disassembly of running RA, which is simply the development workload of our debugger. The previous discussion mentioned the execution of including and RA, but didn't elaborate on how they are organized and executed. In fact, each including organizes some RAs in a tree structure in memory. These RAs can be queries, filtering, aggregation, etc. And they are organized together according to their dependencies, forming an array tree. When the array tree is executed, they are converted into corresponding pipeline for actual computation and operation. This conversion process is accomplished by calculating the dependencies between enclosings, and the specific conversion relationship is shown above. This tree structure, organization, and conversion relationship design makes the execution of AI efficient and convenient for debugging and optimization. After being converted to a pipeline, IA's evaluate method will recursively call each node. The above code calls the run internal method of abstract relationship pipeline, which retrieves the content of specific columns in a table according to the requirement of IA. Each table is abstracted as a page relation for storage. During execution, each node corresponds to a page relation, and the nodes are connected by data streams. In actual operation, each page relation is loaded into memory for processing. We have learned how to use JDB to control the running of the CodeQL engine AI and orbiting the decompile task of the run. Now let's explore how to find the entry point of each table storage by the CodeQL engine. The CodeQL engine saves the table generated by reading the local database and evaluating the enclosing in the form of page relation to a map. Therefore, we only need to read according to the storage format of the tables in page relation use JDB. And the form of relation is shown at the bottom. In addition, there is specific implementation in our QL debugger. Finally, we made modification to the QL launcher parameters so that it could be allow JDB connections and use the system tuning parameters that are not publicly available in CodeQL documentation. In these parameters, allow the CodeQL engine to record the engine's execution state in test form. This helps us to use dynamic debugger to view previous run encoders, so that I don't have to use JDB to implement the trace functionality. We have already talked about a lot of theoretical knowledge, and now through the following demonstration video, you can more intuitively understand how to use QL debugger and how to debug QL code. Firstly, use CodeQL debugger to start the QL test to be debugged, and use the logdir parameter to configure the directory where the trace file will be placed. And next, use the default configuration to attach the process start by JDB. Okay, it stopped once. And the global sort all of the page relation cosec records the running enclosing, and you can view the I code of this enclosing. We can see the current running IA and step through it. Wait for previous enclosing to execution and extract a specific table from database. Wait. Okay. This is enclosing of scan functions. You can see the value in page relation through watch. This is value. Okay, next step. You can find the previously run IA through the log and check relation between the input and output tables of preceding, including after running. We can see the log file. We can check the input table and output table. The output table will be displayed in log file. Okay, continue. After completion, we can see the query result. That's all for demonstration. We will be open source it soon, so stay tuned. Oh, thanks.